And the last thing we're going to talk about is geometric isomers. So we had diastereomers, right? And then we have diastereomers, and we divide that into epimers or geometric isomers. Now, geometric isomers, they're even though they're under the umbrella of diastereomers, right? They're non-mirror images, but epimers, unlike enantiomers, right? They do not, do not require chiral centers. They do not require chiral centers. And one more thing to note about them is that they're basically restricted, right, in rotation because of a double bond or a ring. They're restricted in rotation because of double bond. I don't know why I put a hyphen there. Double bond or a ring. So I'm going to show you exactly what that looks like. Let's say we have a molecule like this. Right, CH3, CH3, hydrogen, hydrogen. And we have another molecule like this. Same thing. 3. And then we have CH3, hydrogen, hydrogen. So if you look at these two molecules, right, these are what's known as geometric isomers because what? Their rotation is restricted because of this double bond, right? And the only how they differ is you see how their largest groups, right? The methyl groups, the CH3, CH3, right? For this molecule, or let's call this A, let's call this guy B, right? So these two guys, they're known as geometric isomers because you can't really rotate them, right? They're fixed because of this double bond, and we categorize them furthermore. We call them cis or trans, or Z or E. So we categorize these guys even more: cis, right, or trans, or another way to think about it is either we have Z or we have E. So these are ways to categorize your geometric isomers. If you have a double bond, right, and your two largest substituents, if they're on the same side of the double bond, right, so you have the CH3s on both sides of the double bond, we call that cis or Z, right? If they are, and the way to I'll give you guys a little mnemonic to remember it. But if the two substituents, if they're on the opposite side, so you see how the CH3 over here and the other one is all over here, right? We call that trans, and or you can call that E. So cis or Z, you can call that like the same. I don't know. This is stupid, but same side. Get it? Same side. Or E. I don't know. Opposite sides. I don't know who comes up with this, but opposite sides. But it helps to remember them. So if the two biggest substituents, right, if they're on the same side, we're gonna call them cis or Z, or Z configuration. If they're on the different sides, we're gonna call that trans configuration or E configuration. I'm sorry. So yeah, that's basically it for isomers. Oh, and actually one last thing, we're gonna talk about meso compounds, right? So all those things that we talked about, geometric isomers, we talked about enantiomers, we talked about diastereomers, blah blah blah. So any one of them, we can categorize it as a meso compound, or meso, however you pronounce it, meso or meso compound. So it's another term to categorize something, and in order for something to be a meso compound, that molecule, it must contain chiral centers. That's one thing. It must contain chiral centers, right? It must have a internal plane of symmetry. So it needs to have a internal plane of symmetry. and yeah, and then what do you call it? Symmetrical chiral centers must have opposite configurations. So it must have a it must have a plane of symmetry, and wherever the two sides of it, they should have opposite configurations. Let me just show you guys, and then you'll know exactly what I'm talking about. So let's say we have a molecule like this, wedge, dash, wedge, dash. Add a methyl group over here. Add a methyl group over here. Hydrogen, hydrogen, bromine, bromine. All right. So first things first. In order for something to be categorized as a meso compound, it has to have chiral centers. Does it have chiral? Yeah, right here. Here's one chiral center. Here's another chiral center. Now, in order to be a meso compound, it also has to have a plane of symmetry. Does it? Well, let's look. If you look at it like this, right? You see how it does have a plane of symmetry. Br, Br, hydrogen, hydrogen, methyl group, right? So, and the last thing I told you is that those chiral centers, right? They have to have those chiral centers. They have to have opposite configuration, and that I'm talking about the whole S and R situation. So, if you actually go through it and check the chiral centers on this one, you'll see this has a S configuration, and this one has a R configuration. So we would call this guy right here, this whole molecule, we would call it a meso or a meso compound. And another example, I'll leave you guys with this, is something like this. CH3, hydrogen, CH3, hydrogen. So this is just another example. Now, can you guys see this? Okay, cool. Does it have a plane of symmetry? Yes, right down the middle, right here. Does it have chiral centers? Yeah, right over here. This is a chiral center. This is also a chiral center. And does it have opposite configurations? Well, yeah, it does. If you actually go ahead and go through it, and you'll find out that this one is a S, and this one right here is a R. So if you guys, like I said, if you guys are having trouble with the whole R and S configurations, look for the video on my channel about chirality and all that stuff, and how to, find out if it's a S or a R. But yeah, keep in mind, meso compound is just a way to giving another way to categorize. Like, we're gonna call this guy a meso compound. So this is kind of something separate from the whole little flow chart that I made for you guys. But yeah, that's it that's it for this video. If you guys have any questions, comments, let me know, and I'll see you guys in the next video.